Welcome back to the Deep Dive, where we take complex engineering blueprints and, well, high-level specifications and turn them into clear, actionable insights for you. Today, we're doing a strategic deep dive into the future of flight power. Specifically, the P13 series parallel hybrid propulsion system. And this isn't just a discussion of components. This is a review of the top-down engineering solution designed to eliminate the single biggest obstacle facing the air mobility revolution, range anxiety, and to unlock the entire regional air mobility market.
Exactly. We're looking at the foundational blueprint issued by the Office of the Senior Aerospace Propulsion Architect. In this document, it's a masterclass in applying systems engineering rigor. It uses a MECE structure, mutually exclusive, collectively exhaustive, to define every single component and function, and it's all guided by one non-negotiable mission: achieving airworthiness safety targets while delivering true commercial viability beyond current electric limits. Our goal is to unpack the why behind this architecture.
Okay, let's unpack this then. Let's start with the fundamental physics problem that drives this entire design choice. Everyone is rightly excited about pure electric eVTOLs, but there is a hard strategic ceiling they run into, isn't there? The range ceiling. Why is the promise of pure electric currently capped by, well, the immutable laws of physics?
It starts and ends with energy density. When you approach a complex system design from a top-down perspective, you just have to accept the limitations of your energy source. Current state-of-the-art system-level lithium-ion battery energy density. It hovers in the range of, say, 150 to 240 watt-hours per kilogram. That's the chemical storage capacity.
And that's a great number for ground vehicles, but for anything that has to fight gravity, that's a killer, isn't it?
It is. Now compare that to traditional aviation fuel, Jet A. Even when we calculate the effective energy density, which, has to account for the thermal inefficiencies of converting fuel into useful mechanical energy, Jet A still offers a roughly 40 times advantage in specific energy.
40 times.
40. We're talking about an effective specific energy of approximately 12,000 watt-hours per kilogram.
40 times the energy punch per pound. That number alone just shows the strategic gap. If I need to power a regional flight, I'm going to be penalized heavily for choosing batteries over fuel.
And that's the commercial cliff edge. That physics differential translates directly into mass allocation. To achieve any useful regional range, a pure battery electric eVTOL has to allocate 30% or more of its maximum takeoff mass, the MTOM, just to the battery pack.
Wow.
Think about that. Almost 1/3 of the aircraft's potential capability is dedicated just to carrying its energy. That enormous mass allocation fundamentally cripples both the available payload for passengers or cargo and, of course, the effective mission range.
So if pure electric is limited, where does that critical tipping point lie that the P13 is designed to cross?
The high-profit, high-utilization market, what we call regional air mobility, or RAM, that really lives between 150 and 200 kilometers. This is the segment that demands high asset availability, flexibility, crossing between smaller hubs or city centers. Pure electric vehicles just cannot reliably or profitably serve this segment. Once you factor in the required energy reserves for headwinds, delays, emergency contingencies, the battery weight becomes untenable.
Okay, so the P13 system is the strategic engineering answer to this commercial dilemma. How does this specific series parallel architecture bridge that 40 times density gap while still meeting the insane demands of aviation?
It's all about intelligent integration, purely. The P13 is a sophisticated hybrid that uses a dynamic blend of mechanical and electrical power. It specifies two primary power positions. The P1 position houses the thermal propulsion unit, that's either an advanced internal combustion engine or a gas turbine, and it's paired with an integrated starter generator. And then the P3 position is the primary high-density propeller drive motor. By combining these, the system leverages the energy density of fuel for range while retaining the instant torque and high-safety redundancy of batteries for critical phases like takeoff and landing.
And this combination is engineered to achieve that holy grail of aerospace safety, the ESE-SE VTOL Enhanced Category Safety Target. I want to stress this number for you. A catastrophic failure probability of less than 1 in a billion. That's less than 10 to the minus 9 per flight hour. That is the true north for every single decision in this blueprint.
It is the absolute defining metric. The entire system is architected around meeting that 10 to the minus 9 safety target through fundamental redundancy principles, which we'll get into. And the technological core enabling this level of performance and control is the electrical backbone, an 800-volt high-voltage direct current bus. The HVDC bus. This is integrated with cutting-edge silicon carbide power electronics and smart algorithms, model predictive control for precise, instantaneous energy management.
Okay, Let's dive into the guts of the machine now. Part 1. The P13 architecture and functional definition. This is where that MECE breakdown of the system really begins.
Right. The core concept that defines the P13's brilliance is something called dynamic power decoupling. Most people think of hybrids as either series.
Where the engine is just a generator.
Exactly. Engine charges the battery, battery powers the motor, or parallel, where the engine and motor both drive the wheels or the prop. The P13 is neither. It's a dynamic blend. It uses a single-core power-splitting mechanism, a planetary gear set coupled with the K0 decoupling clutch to seamlessly integrate the mechanical power path and the electrical power path. The power flow isn't fixed, it's dynamically allocated by the VCU.
So that K0 clutch is like the central nervous system, deciding whether the thermal engine is driving the propeller, generating electricity, or just sitting idle. Let's look at the 4 core physical subsystems that enable this complex dance.
We can categorize them. First, the Thermal Propulsion Unit, the TPU. This is the main source of energy for that long-range segment. Its dual role is critical. Role 1, provide direct mechanical drive to the propeller shaft in the most efficient cruise modes. Role 2, drive the P1 generator for series operation or charging the battery when mechanical drive isn't needed.
Okay, and next, the P1 ISG. This unit sounds far more complex than a standard car starter generator. What does it contribute beyond just basic power generation?
Oh, the P1 integrated starter generator, the ISG, is mounted directly to the TPU output shaft. And yes, it starts the engine and generates stable 800-volt HVDC power, but its third and perhaps most sophisticated function is active torque fill.
Active torque fill, what does that mean?
This is crucial for aircraft stability. Internal combustion engines, particularly piston types, they naturally produce cyclical torque pulses, little vibrations and slight power surges every time a cylinder fires.
Which in a plane translates to noise, vibration, and unwanted stress on the airframe.
Precisely. The P1 ISG, using these high-speed MPC algorithms, instantly detects and counteracts these pulses. It does it by injecting or absorbing minuscule amounts of torque from the electrical bus. It's essentially a high-speed electrical shock absorber for the engine's power pulses.
That's incredible.
And this dampening dramatically improves flight quality, stability, and critically protects the sensitive propeller gearbox and control linkages from unnecessary dynamic load variations. It enhances the airworthiness lifespan.
So the P1 ISG is the key bridge between the relatively crude mechanical output of combustion and the hyper-smooth, precise demands of rotorcraft flight control. Okay, moving to the linchpin, the K0 decoupling clutch.
The K0 decoupling clutch is the mechanical heart of the mode switching. Its job is to physically engage or isolate the entire thermal energy chain, the TPU and the P1, from the primary propeller shaft. Its reliability and response time are defined as safety critical. The specification demands extreme precision and speed. The VCU needs that clutch to execute a coupling or decoupling sequence in less than 200 milliseconds.
200 milliseconds.
To ensure the transition is seamless and completely undetectable to the flight control system.
Because if that clutch hesitates or grabs unevenly, you could introduce massive harmonic vibrations into the drivetrain at altitude that really underscores the need for that precision.
Absolutely. And finally, we have the P3 propulsion motor. This is the unit that defines the EV in eVTOL. It's the primary electric drive. It provides 100% of the thrust for vertical lift and precision maneuvering. And when the TPU is engaged in parallel mode, the P3 motor transitions to an auxiliary role, offering maximum power boost capability.
This strategic setup gives the Vehicle Control Unit, the VCU, 5 distinct operational personalities, which is all managed by its state machine. Let's walk through a typical mission, starting with, say, a city departure.
Okay, so we start with Mode I, pure electric or eHEVER. This is the zero-emission mode required by urban environments. The K0 clutch is open, TTU is off. Power comes solely from the battery, feeding the P3 motor for that vertical takeoff. This keeps the acoustic footprint minimal and satisfies those noise-sensitive urban regulations.
Right. And once we clear the noise-sensitive zone and begin our transition to cruise altitude, we might enter a phase where we need fuel economy, but don't want the complexity of synchronizing the engine to the prop speed.
That leads us to Mode 2 series mode. The K0 clutch remains open. The TPU is running, but it's dedicated entirely to driving the P1 generator, staying physically disconnected from the prop shaft. The sheer engineering advantage here is decoupling. The VCU can command the TPU to run continuously at its best specific fuel consumption sweet spot. the BSFC.
Its most efficient RPM.
Exactly. The specific RPM and torque where it maximizes fuel efficiency, regardless of what speed the P3 motor needs to turn the propeller. It's maximum fuel economy for sustained climbing or, say, loitering.
That's great for charging the battery or climbing efficiently, but the moment we are in horizontal flight and we want maximum range and minimal energy waste, we enter the most critical mode for commercial success.
That is mode 3, parallel cruise. The K0 clutch is closed, mechanically linking the TPU directly to the propeller shaft. The TPU provides the majority of the thrust. The P3 motor is either in standby or provides a minor electronically controlled assist. The strategic advantage here is just undeniable. You entirely eliminate the energy conversion losses.
You mean the AC to DC conversion in the generator and then DC to AC in the P3 inverter?
All of it. You eliminate those losses.
And eliminating those energy conversion steps, which even at 99% efficiency still cost you useful power, is where you harvest massive range gains.
Absolutely. We're targeting extremely high mechanical transmission efficiency, up to 98%. That mechanical transmission bypasses the electrical losses, and that translates into a guaranteed 10 to 15% energy efficiency improvement compared to running in series mode.
That margin is the difference between serving a 150-kilometer route and serving a profitable 200-kilometer route.
That's the business case right there.
So Mode 3 is the moneymaker. But for safety, you need an instant response capacity. If Mode 3 is running and the pilot needs maximum evasive power, we hit Mode 4.
Mode 4, dual source power boost. This is the safety override. The K0 clutch remains closed. The VCU slams the TPU to its maximum power setting. AND simultaneously commands the P3 motor to provide its maximum supplemental torque from the battery. This layers the mechanical and electrical power, achieving short bursts of maximum thrust. This is reserved for immediate high-demand maneuvers, executing a missed approach, a go-around, avoiding a collision, or surviving a critical one-engine inoperative scenario.
Where the remaining systems have to compensate instantly.
Instantly.
And finally, the VCU has to manage the return home, ensuring we have enough battery juice to execute that quiet mode-I landing. Which brings us to Mode V.
Mode V, charge sustain. This runs strategically during cruise. While the TPU is driving the prop shaft in parallel cruise, the VCU identifies any excess TPU cruise power generated that isn't strictly needed to maintain stable horizontal flight, and it routes it via the P1 generator to recharge the battery mid-flight. The core mission of this mode is to guarantee that the battery state of charge is sufficient for a safe, noise-abated, pure electric vertical landing, no matter how long the regional cruise segment was. That operational flexibility is paramount.
That complexity shows that P13 is not a simple hybrid. It's a fully dynamic energy manager. It's clear that the foundation for all this complexity is the rigorous adherence to safety standards, which leads us to Part 2. Guiding design principles. Let's start with that non-negotiable 10 to the minus 9 safety target.
That extreme probability target is the reason we must adopt the no single failure principle. In aerospace, this is more than a guideline. It's a design constraint. The failure of any one component, mechanical, electrical, or software, must not, under any circumstance, lead to a catastrophic outcome.
Give us an example of how that trickles down to a specific component.
Okay, take the K0 clutch we just discussed. Because it's the point of mechanical connection, it's a high-risk component. The specification demands that the K0 clutch incorporate a fail-safe open mechanism. If the control system, the power, or the clutch actuation mechanism fails, the mechanism must default to the open position.
So it automatically disconnects.
It reliably isolates any mechanical or thermal failure in the TPU or P1, say a gearbox seizure or a massive engine overheat, and prevents that fault from propagating and shredding the primary propeller shaft.
And the high-level strategy to hit 10 to the minus 9 is what you termed dissimilar redundancy. Can you elaborate on why just having a backup isn't enough?
Right. If we connect this to the bigger picture, using identical backups carries the risk of a common cause failure, a CCF. Imagine if your flight control computer had two identical processors running the exact same software. If there's a subtle software bug, both processors fail at the exact same moment.
Or the backup fails for the same reason the primary did.
Dissimilar redundancy solves this by using two fundamentally different methods to achieve the same goal.
Which in the P13's case means the chemical energy path and the electrochemical energy path.
Precisely. We are leveraging the chemical energy of jet fuel converted by the TPU and the electrochemical energy stored in the battery. Their physical, chemical, and thermodynamic failure modes are fundamentally different. A fuel line blockage doesn't affect the battery's state of power. A thermal runaway event doesn't cause a gas turbine to seize. Because the root causes of failure are topologically distinct, the probability of both systems failing simultaneously drops dramatically, pushing that failure rate below the mandated 10 to the minus 9. This is arguably the most elegant strategic decision in the entire blueprint.
It's a survival mechanism hardwired into the system's topology. Okay, moving to the second pillar. The electrical and mechanical principles, starting with the 800-volt HVDC system. I know the weight savings are key, but what are the precise technical benefits of going to 800 volts?
This is a decision driven entirely by maximizing power density and minimizing mass. Compared to traditional aerospace or automotive 400-volt systems, adopting 800 VDC is transformative. By doubling the voltage at a fixed power level, you instantaneously have the current required to deliver that power.
And the result of having the current.
Since power loss in a cable is proportional to I squared R, the square of the current halving, the current immediately reduces resistive losses by 75%.
75%, that's huge.
Less loss means less heat to manage, increasing efficiency. But the biggest win for aviation is the physical weight reduction. With lower current, you can use thinner, lighter gauge copper cabling. The spec calls for a reduction in copper harness weight of approximately 45%. When every kilogram means lost revenue or range, that 45% saving is strategic gold.
That's a massive return. But complexity has a price. To handle 800 volts efficiently, you need specialized hardware, which brings us to the silicon carbide or SiC inverter technology. Why SiC over standard silicon?
We need incredibly fast, efficient switching. The P3 inverters must use 6 MOSFET power modules because they can handle higher temperatures and switch significantly faster than traditional silicon-based IGBTs. 6MA enables efficiency greater than 99% and, crucially, a switching frequency over 40 kilohertz.
Why is 40 kilohertz so important beyond just efficiency?
High switching frequency allows the magnetic components, the inductors and capacitors, to be much smaller and lighter. If you switch at 5 kilohertz, your filters need to be large and heavy. At 40 kilohertz, the filtering components shrink dramatically. This reduces system mass and controls harmonic noise more effectively. This is where high power density, that 13 kilowatt a kilogram target, is achieved by leveraging 16 to shrink the supporting electrical infrastructure.
Here is where the aerospace environment pushes back, though. If we're flying above 10,000 feet, the air itself becomes a problem for high voltage, dictated by Paschen's law. Can you demystify this?
It's fascinating, isn't it? How design must account for atmospheric conditions. Paschen's law dictates that the voltage required to cause an electrical breakdown in a gas changes based on pressure and the gap distance. As the aircraft climbs, the air pressure drops. Low air pressure means low air density, which dramatically reduces the dielectric strength of the air. The air is less effective as an insulator. This increases the risk of subtle, slow electrical damage called partial discharge.
So if the breakdown voltage drops, you start getting these micro sparks in connectors and wiring bundles, even if they aren't fully shorting. What is the long-term danger of that?
The danger of PD is insidious, not instantaneous. Partial discharge is localized. It's not an immediate arc flash. But those tiny discharges, they emit ozone and high-energy UV light. These byproducts chemically attack and slowly degrade the polymer insulating materials, the wire coatings like ETFE or PEEK insulation on bus bars. Over thousands of flight hours, this chemical etching reduces the physical integrity of the insulation.
And they could lead to a catastrophic short circuit or component failure later in the aircraft's life. So the P13 architects aren't just designing for today's flight, they're designing for 10 years of atmospheric degradation. How is this mitigated physically?
Through rigorous physical design and testing, every high-voltage component must increase its physical design margins. Creepage, which is the distance across the surface of an insulator.
Long path.
Right. And clearance, which is the direct air gap distance. Crucially, all components must pass stringent partial discharge testing, where the PD initiation voltage is certified to be greater than 1.5 times the peak working voltage.
So 1.5 times 900 volts.
That's the safety margin. It ensures the insulation remains robust, even in the thinnest air at maximum certified altitude.
That deep focus on long-term chemical degradation really shows the difference between automotive and aerospace engineering standards. Okay, finally, the third pillar, the certification-driven process.
The entire design philosophy must adhere to the aerospace gold standard. The V model development, which is SAE ARP 4754. The V model structure forces a top-down approach to decomposition and a bottom-up approach to verification.
When you say two-way traceability, what does that mean for an architect trying to prove the design?
It means we must prove to the regulatory body that every single line item in the P13 blueprint can be traced back to a high-level aircraft requirement, and that every high-level requirement like must achieve safe vertical landing after engine failure has been fully decomposed into testable component requirements. For example, if the high-level requirement is 10 to the minus 9 safety, you must trace how the specific material selection for the 60 inverter cooling manifold contributes to that goal. This systematic process is the only way to quantitatively demonstrate airworthiness compliance.
That process is the key to minimizing risk long before the first flight. Now let's move into part 3 and define the hard metrics of success, the component requirements and integrated system specifications. What are the key performance indicators, the KPIs, that this P13 system must meet to be considered successful?
These KPIs are the performance quantification. They are ruthless. First, we look at overall efficiency. The system-level power density, that's total integrated power divided by total mass, must be greater than 2.5 kilowatts per kilogram. But the real driver of vertical lift is the P3 electric motor. Its target power density must exceed an extremely aggressive 13 kilowatts per kilogram.
13 kilowatts per kilogram. That's only achievable through those 800-volt, 40 kilohertz CC designs we just discussed.
It is, and since we're using fuel for range, the TPU efficiency is just as critical as the motor density.
Absolutely. The TPU-specific fuel consumption targets are the hard gate for commercial viability. For a piston engine, it must be less than 230 grams of fuel per kilowatt-hour output. If it's a turbine, less than 350 grams per kilowatt-hour. If the system fails to hit those numbers, the weight of the fuel you have to carry negates the range advantage and the project fails its economic mission. Let's talk about the brain, the VCU. Since it's managing 5 complex modes and juggling mechanical and electrical power, what makes its software integrity so critical?
The VCU is the ultimate torque arbitrator and mode supervisor. It's making safety-critical decisions about power distribution in real time. Therefore, its control logic and core energy management software must meet DO 178C Design Assurance Level A, DALA.
That's the highest level of software integrity, reserved for systems where failure would cause catastrophic loss of the aircraft.
Correct. And for a control system that needs to react to an engine failure or a sudden power boost command, speed is paramount.
What's the time constraint here?
The required end-to-end latency, from the moment the flight control computer sends a torque command to the moment the physical P3 motor or K0 clutch executes that change, must be less than 10 milliseconds.
Less than 1/100th of a second.
That tightness ensures the aircraft's stability control loop can always rely on an instant power response. Any latency greater than that could introduce dangerous oscillation or delayed reaction to pilot input.
And the VCU's control over the K0 clutch transition is equally demanding.
It requires extreme precision. During clutch engagement, the VCU has to synchronize the rotational speeds of the TPU output shaft and the P3 rotor shaft to within a tolerance of just plus or minus 50 RPM.
Just 50 RPM.
If the synchronization is off by more than that, the engagement creates a massive dynamic shock loading across the entire drivetrain, which accelerates component wear and compromises structural integrity.
That is precision engineering at its finest. Let's shift our focus to the energy storage system, the battery and its management system. The safety requirements here are the defining technical challenge of the entire electric side.
Indeed, safety means rigorous thermal runaway containment. The battery pack must pass RTCA DO 311A containment tests. If a single cell is thermally destabilized by puncture, overcharge, whatever, that event must be contained for a minimum of 15 minutes.
Why that specific 15-minute firewall?
The 15-minute window is the critical time required for the crew to detect the thermal event, receive the confirmed BMS warning, execute the emergency checklist, and perform a full, safe vertical landing or transition to an emergency flight profile. The spec is uncompromising. Within those 15 minutes, there must be no propagation of heat, fire, or high-pressure gas to adjacent cells or modules, and, crucially, no release of toxic gas or smoke into the cabin or avionics bay.
That places an enormous burden on the cooling plate design, insulation, and venting systems within that battery enclosure. Beyond physical containment, what is the BMS's most important job during flight?
It's the constant, accurate estimation of the state of power. The SOP, while state of charge, how full the battery is monitored. The SOP is the non-negotiable basis for mission-critical decisions. The BMS must accurately predict the maximum power the battery can deliver over the next 60 to 120 seconds.
I see. So if the pilot needs to initiate a high-power go-around, they must know with absolute certainty that the battery can sustain that maximum thrust for that critical 2-minute window.
Yeah.
The P13 is essentially a thermodynamic nightmare. You have hot combustion engines, medium hot electric motors, and batteries that have to stay cool. How is the integrated thermal management system architected to manage these highly divergent needs?
This requires a highly sophisticated multi-zone liquid cooling architecture. Applying the MECE principle, we partition the thermal requirements into 3 specific, non-overlapping temperature loops.
Okay, walk us through those 3 thermal loops.
First, the high temperature loop operating above 90 degrees Celsius. This is dedicated solely to cooling the TPU engine components and the exhaust gas heat exchanger. The unique detail here is efficiency. The system uses the fuel itself as a primary heat sink.
You're kidding.
No, the fuel is routed through the cooling system to absorb waste heat before injection. This preheats the fuel slightly for better combustion efficiency while simultaneously cooling the engine. It's an elegant energy recycling solution.
So killing 2 birds with 1 stone,
Oh.
cooling the engine and slightly boosting the energy content of the fuel before use.
Exactly. Next is the mid-temperature loop, running at 60 to 70 degrees Celsius. This loop is tasked with cooling the P1 and P3 electric motors and the high-power SINS inverters. This system uses liquid cooling but integrates skin heat exchangers, or SHX. These are heat transfer mechanisms embedded directly into the non-load-bearing sections of the aircraft's fuselage skin.
That sounds complicated for maintenance, but strategically brilliant for aerodynamics. Why the SHX integration?
It eliminates the need for large, drag-inducing external radiators. The waste heat is passively and efficiently exchanged with the ambient airflow moving over the fuselage. It minimizes aerodynamic drag, which directly boosts the cruise range.
Makes sense.
And finally, the lifeblood of the electric system, the batteries.
Which have to be kept cool.
That is the low-temperature loop, kept below 40 degrees Celsius. Batteries require tight temperature control, ideally between 25 and 35 C, to ensure longevity and maximum power delivery. In hot operational environments or during fast charging on the ground, this loop requires active cooling, utilizing a sophisticated vapor compression system, basically an aerospace-grade refrigeration unit, to maintain the precise thermal environment required for cell health.
Managing 3 loops with 3 different fluids, 3 temperature ranges, and 3 different rejection methods, fuel, skin, and refrigeration, is a huge integration challenge. Which leads us logically into part 4, interface requirements and validation pathway. The components need to talk to each other perfectly.
They need to communicate with microsecond precision and unquestionable integrity. Starting with the digital side, we can't use standard commercial Ethernet. For flight-critical communication, the VCU sending torque commands, the system must use deterministic, high-integrity protocols like TDataNet or AFDX.
What does deterministic mean in this context, and why is standard Ethernet not good enough?
Deterministic means the time taken for a data packet to travel from point A to point B is fixed and guaranteed, often down to the microsecond level. Standard Ethernet uses collision detection, which means data packets might experience variable latency or delays. For the VCU to synchronize the P1 and P3 torques, the command signals must arrive at the components with 0 jitter. Ethernet ensures that microsecond level synchronization, which is essential for, say, a Mode 4V power boost.
That guarantees the communication backbone is as reliable as the physical hardware. Now let's talk about the physical safety interfaces designed to protect ground crew and internal systems from that 800-volt bus.
The primary protective requirement is the high voltage interlock loop, the HVIL. This is a non-negotiable safety feature required on all high voltage connectors and service panels. The HVIL uses low-voltage auxiliary pins embedded within the connector housing. If a technician forgets to fully secure a connector, or if vibration loosens a cable mid-flight, the system instantly detects the break in that low-voltage auxiliary loop.
And what must the system do when that circuit is broken?
It must automatically and instantly cut the high-voltage source opening the main DC contactors within a rapid 50 milliseconds. This prevents accidental electrocution or catastrophic irksing.
So if a cable comes loose, it shuts everything down instantly.
Instantly.
That's protection against immediate failure. But what about the slow degradation we talked about with partial discharge? How do you monitor internal insulation health?
That's the job of the Insulation Monitoring Device, or IMD. The IMD is an active device integrated into the HVDC system that continuously monitors the insulation resistance between the live HV bus and the aircraft's metal airframe. It injects a continuous pulse train to measure that resistance.
And what's the warning threshold?
The specification requires the warning threshold to be set rigorously at 500 ohms per volt. For an 800-volt system, that means if the insulation resistance drops below 400,000 ohms, the IMD triggers a warning in the cockpit and maintenance logs. This provides crucial pre-failure intelligence, allowing maintenance crews to fix a looming safety threat like PD damage before it progresses to an electrical fault.
This entire specification is clearly designed for global certification, which means targeting the triple regulatory alignment.
Yeah.
EASA, FAA, and SEAC.
That's right. And the complexity of hybrid power means satisfying different regulatory emphasis areas. The EASA focus is on compliance with SC VTOL 01 enhanced category. For hybrid systems, this means strict adherence to SCE 19, demanding explicit proof of overspeed protection and robust fragment containment.
And what's the FAA prioritizing, this new special class of aircraft?
The FAA focus follows the special class path, but their key area of concern is battery safety integrity, relying heavily on DO311A standards. For them, the absolute non-negotiable requirement is the no propagation standard, proving via testing that thermal runaway stops at the cell level.
And finally, the SEAC has emerging domestic standards that must be incorporated.
Right. The ACT references the forthcoming 2025 airworthiness regulations for power-lift aircraft. And we note that the SAC places special emphasis on data link security and national standards for battery thermal defense. Targeting all three adds significant cost and complexity, but it unlocks global market access.
That sets the stage for the rigorous validation and verification process, the right side of that V model. This is where the paper specification becomes a certifiable flying reality.
This V&V process is the systematic de-risking strategy. It starts by integrating software and hardware in a simulated environment, hardware-in-the-loop testing, HIL testing. This involves taking the actual flight-ready VCU controller, a black box running the DALA software, and connecting it to a massive real-time simulator that models every physical characteristic of the TPU, P3 motor dynamics, and battery response.
And the purpose of HIL is not just to see if it works, but to see if it breaks safely.
Exactly. AAO allows for massive failure injection tests. We intentionally simulate every conceivable fault: a sensor reporting the wrong temperature, communication packet loss on the T-Tethernet link, excessive actuator delay, a sudden power sag. This is how we validate the VCU's resilience and its fault handling logic under conditions that are too dangerous or destructive to replicate on a physical aircraft. It's the process of proving the software meets DALA.
But simulation can only go so far. We eventually need to test the real physical components interacting with each other. That takes us to the Ironbird.
The Ironbird is the gold standard of pre-flight risk reduction. It involves constructing a full-size ground test rig with every critical component: the TPU, the P1, P3 electric propulsion units, the carry-sear clutch, the actual battery packs, and the full TMS liquid architecture. It replicates the entire drivetrain topology.
What are the key verification tasks performed on the Ironbird?
Two critical areas. First, mechanical durability. We perform thousands of mode switching cycles, mode 1 to mode 3, mode 3 to mode 4, to verify the long-term durability and synchronization robustness of the K0 clutch and gearbox under simulated flight loads.
And second,
environmental proof. The Ironbird is placed inside an environmental chamber for high-altitude simulation. This is the non-negotiable step to verify the 800-volt system's partial discharge characteristics in a low-pressure, thin-air environment, proving those 1.5x insulation margins hold true.
And finally, the hardware has to survive the real-world environment.
That's the final stage of physical certification. Environmental stress testing, per RTCA DO 160G. This ensures component robustness. Key areas include testing against high-frequency RF radiation emissions, ensuring the sysreverters don't interfere with the aircraft's GPS or comms, and testing resilience against lightning-induced transients. If a component fails under a simulated lightning strike, the entire certification process stalls.
We have covered the physics, the topology, the safety principles, and the testing roadmap. Let's bring it all home now with Part 5, focusing on the non-negotiable acceptance criteria that define success and the commercial implications of this high-level engineering.
These acceptance criteria are the quantified final gate that prove the 10 to the minus 9 safety architecture functions in reality. They are uncompromising.
Criterion 1, proving that dissimilar redundancy works in practice.
Single failure protection. This must be demonstrated under test. If we simulate the physical disconnection or failure of a single battery pack or a single P3 inverter, the flight control system must automatically and instantly redistribute torque among the remaining healthy power sources. The system has to prove it can absorb the shock of that failure and ensure the aircraft maintains stable flight or executes a safe, controlled emergency landing without the pilot needing to intervene beyond standard procedures.
Criterion 2. The smoothness of the power transition.
Mode switching smoothness. During any mode transition involving the K0 clutch, say, e-hover to parallel cruise, the propeller rotational speed fluctuation must be aggressively controlled to less than plus or minus 2%.
Just 2%.
It's a measure of the VCU's synchronization precision. Exceeding that indicates a dynamic stress event that compromises the structural life of the gearbox.
Criterion 3. The hard number for battery survivability.
Thermal containment time. Following single-cell thermal runaway, the heat and noxious energy must be contained within the ESS box for the mandated 15 minutes. That is the absolute temporal firewall protecting the mission and passengers.
And criterion 4. Proving the solution to the high-altitude problem.
Electrical insulation margins. At the maximum certified altitude, we must prove the partial discharge initiation voltage of all 800V components exceeds that critical 1.5 times the peak working voltage. This is the final verification that the component design will not succumb to the atmospheric degradation.
And finally, the validation of the system's brain.
Software integrity. The core energy management software, the EMS, must achieve 100% MCDC testing, modified condition decision coverage. This level of verification is the ultimate proof required for DO 178C DALA compliance, confirming that every single condition and decision path in the safety-critical software has been exercised and verified.
We've established that this is a technological marvel driven by safety. So what does this all mean for the business of eVTOLs? What is the commercial closure argument for adopting this expensive, complex P13 hybrid architecture?
The P13 hybrid architecture is the optimal technological pathway to decisively overcome the current eVTOL battery ceiling. The entire engineering process is guided by a singular principle: airworthiness, safety as the sole criterion. But that safety, achieved through dissimilar redundancy, is what actually unlocks the commercial viability.
Let's address the total cost of ownership implications. Hybrid operation involves fuel, which costs more per hour than electricity. Where's the financial win?
You are correct. Hybrid operations have a higher hourly direct operating cost, estimated around $800 to $900 per flight hour, compared to maybe $650 per hour for pure electric. But the value is realized by looking at the asset holistically. First, hybrids unlock the high-margin regional air mobility routes. They can service missions spanning 400 to 600 kilometers. Routes that pure electric aircraft, constrained to less than 150 kilometers, simply cannot touch. This vastly increases the addressable market and the asset utilization rate.
So, lower revenue per flight hour for pure electric, but drastically limited flight opportunities. Higher cost per flight hour for hybrid, but access to exponentially more routes.
Exactly. Second, and this is where the long-term TCO savings emerge, hybrid operation drastically reduces the depth of battery cycling. The batteries are primarily used for low-cycle, high-power phases takeoff, landing, and emergency boost. They avoid the constant deep discharge cycles necessary for pure electric crews.
And reduced deep cycling extends the usable life of those very expensive battery packs.
It does. Lithium-ion packs are the single largest capital expenditure and replacement costs in an electric fleet, often costing millions. By keeping the packs shallow cycled, the P13 significantly extends the battery's calendar life and cycle life, potentially pushing the replacement cycle out by years. This reduction in long-term capital expenditure makes the TCO over the aircraft's lifespan competitive, especially when you factor in the high revenue generated on profitable RAM routes.
We have seen how the P13 specification turns complex propulsion challenges into an organized MECE-compliant engineering blueprint. It's a masterclass in managing complexity and risk by prioritizing safety through dissimilar redundancy and cutting-edge 800VC technology.
The takeaway for you, the listener, is that this design process is fundamentally about managing complexity and risk to meet a non-negotiable safety target, that 10 to the minus 9, which, rather than inhibiting innovation, is the precise lever that unlocks the economic potential of an entire, previously inaccessible market segment.
So here is our final provocative thought for you to chew on. The P13 design forces us to fundamentally reevaluate the true cost of zero emission. Is the optimal future for aerial mobility defined by sacrificing operational range and market access to pursue limited-range, pure electric vehicles? Or is the more pragmatic and commercially superior path to deploy highly efficient, highly redundant hybrids? By integrating fuel intelligently to create operational flexibility, these systems guarantee superior range and that non-negotiable 10 to the minus 9 safety guarantee. The P13 suggests that market viability is found not in eliminating combustion entirely, but in integrating it smartly.